meet all of you, I think. Alette wasn't there, but last night. And I'm changing hats, and I'm speaking to you as not the playback actress, but as the director of the Simons Institute. And I want to welcome you all to the Simons Institute. And as you probably know, this is a place dedicated to researching theoretical computer science, and in particular to collaborative research. So we have, we've been working, we've been open for 10 years. It's a generous grant from the Simons Foundation that opened this Center for Theoretical Computer Science. People come here for programs that are dedicated really for research that is grounded in theoretical computer science. Sometimes it goes to other fields like neuroscience, like physics, and so forth, and engineering. But really the principles are foundations of computer science, which I think you're all students of this discipline, given the title of the theoretical Women in Theory. So welcome, and I hope to see you all throughout the years going forward when you do research. And you know, yesterday Tal had this story about her voice, and I too have had COVID within the last 2 weeks. I'm totally negative, but I'm mentioning that not just because I want to share with you my personal experiences, but we recommend you all wear masks. You do whatever you want. We don't have a rule here. The city of Berkeley does not have a mask mandate, which means that we can't force you. But I think it's a good idea. The reason I'm not wearing it because I just had COVID. So I have like a free ticket out of jail. And also I'm the speaker. Okay. So I was just debating a little bit what professional talk to give here, something older or something newer. And I decided really to err on give you a talk that I've been giving in the last couple of years. So this is not very new, but I think it's sort of more general and more interesting. And I understand that there's a significant number of you who's only first or second year student, if that's correct. So how many of you are first year students? And how many of you are second year students? Okay, so I think I have it right. All right, so the title of my talk is how to address the growing distrust actually in algorithms with more mathematics, so with more theoretical computer science. And as you see, I have a picture here, not just of the Simons Institute, but also of a company that I co-founded. And the reason is not because of the research is related in any way, shape, or form to the work that the company is doing, but just because I think that one of the things that probably is a big distinction between faculty, men and women in computer science. Is there a problem with the sound? Something about me maybe touching my pocket. Get another one? Okay. Let's hope this is better. One of the big distinctions is that I've noticed over the years, and that might not be true already for your generation, but certainly was true for my generation, is that a lot of the guys at some point also did not just continue doing exactly what they did all the time. Not that there's anything wrong with it, that might be the right thing to do in terms of you know, going more and more and doing the research, but they've also diversified their interests. And sometimes they opened companies, sometimes they went for a few years to industry and went back. And in the spirit of exploring your options, I think it's interesting that that was much more the case for I mean, it was very gender different. So I just wanted to say that I, in particular, do have a start of this was very late in the game compared to my colleagues, and who knows how it's going to do. But just for sake of information, that's also something that's open for you later on, and you're allowed to think in the same way that your colleagues do. All right, so to the topic of the talk. So machine learning algorithms. So we all know this is an old picture, but this is a conference of theoretical computer science. Machine learning really is, in my mind, in the intersection of these three: artificial intelligence, theory, you know, statistics. And you know, the only common thing that you need to know for this talk, that when I talk about machine learning, I mean algorithms that learn from data, make predictions on data without being explicitly programmed. So we do know that this availability of data in many different walks of life has changed really everything in health prediction and even decisions of what to do, finance, economic growth, infrastructure, how we drive, which roads we take, how we use electricity, and obviously in the areas of the machine learning researchers mostly do empirical work in vision and natural language processing, in security threat prediction, and these days, of course, or in some sense, when I say these days, it's when this talk was written, which is about a couple of years ago, where these whole questions about policing, where to send police cars, whether to let people out on bail or not, whether to give you credit or not, or to accept you to school or not, was being decided more and more by automatic algorithms, so machine learning algorithms. And that caused huge debates because whether it's correct to have bail this way, to decide whether to send police car that way. The real kind of high order bit is that having a lot of data means that there's a sudden shift of power from the hands of whoever used to make decisions before into the hands of whoever has enough data to make decisions based on this data. So given that there is a sudden shift of power, it's very interesting for us, I think, as theorists, to say, wait a second, is this being done in a principled way? Is there something theoretical we can say about it? And so on one hand, there's a lot of algorithms are being developed there, and it's extremely exciting because they're doing things by a large extent much faster and seems to be more accurate and then it's been done before, but there's very little theoretical analysis of it. And as a result of many things, there's a huge distrust in these algorithms. So on one hand, there's this great development that gives a lot of opportunity for us to study and opportunity for society to grow. On the other hand, there's like a societal move that says, wait a second. And that's a good thing, I think. So I want to talk about that. And I want to talk about how can we address that with sort of more math, more theory. So the kind of perfect example for that is the bail issue. And California had this Proposition 25 a couple of years ago, which was to replace cash bail. So this was on the ballot with, instead of, when there's a suspect and you want to release him from jail, and if it's in the right amount of money, they'll pay and they can be released temporarily till trial, to say that there's only going to be a decision, which is I let you out on bail or not. It has nothing to do with money. You don't have to pay. But an additional thing was that this would be decided, or at least assisted to a large extent, by a risk assessment system, by an algorithm. An algorithm would look sort of at the past data, at the profile of the suspect, and give a recommendation whether this person should be released from bail or not. And by and large, the expectation is the judge would take it as an advice, but we couldn't really see, if we roll the steps forward a few years, it's going to be just automatic, right? That was the proposal, and it did not pass. So, which was surprising because it was already on the books and it was just a question of approval, and it did not pass. Surprising or not, the debate was like this. The supporters said, obviously, cash bail is not, it's not fair. It's distinguishing between people on economic basis, which is usually translates to racial basis. Why should rich people get out of jail and poor people not? And opponents, of course, first of all, were people in the bail industry, which is obvious because they stand to lose money. But the more interesting opponents were those who said that this is the fact that it's going to be a risk assessment system is going to make this worse and not better. So specifically, they were saying things like civil rights advocate, cash bail is fundamentally flawed, but while algorithms can pitch you a song, sell you a toaster, they should not be used for release decisions. The factors considered for release will still leave people of color being held at trial at disproportionate rates. So Proposition 25 is further from the existing problem, but no closer to the solution. That was really the grounds for why this did not make it. I said that it was a surprise. In some sense, maybe not so much of a surprise. We had a workshop here called Wrong at the Root. This is 2019, so as I told you a few years ago. Racial bias and the tension between numbers and words in a non-internet data. So they're saying in this workshop, it was mostly the computer scientists, but a lot of people from law and policy. And what they were saying was that the pervasive use of algorithmic risk complicates or undermines many bedrock democratic values. So if you talk to any of the people in law and policy at that time, I think it's changed since, their feeling was that we are going to do away with a lot of progress that's been done. So by the fact that we're going to replace things by algorithms without scrutinizing them, without really looking at how these algorithms were developed, whether they were looking at biased or unbiased data, whether anybody controlled those algorithms, and these algorithms were going to become the new law, then now they will be worse than before. So there will be nobody that scrutinizes it. They might make these decisions which are even worse than what a judge would have made before. And in general, the reason that they reached this conclusion was a complete distrust of computer scientists. So on one hand, there were these computer scientists who really want to do good. So there are people interested in fairness research and how to make algorithms more fair, whatever that means, some intuitive notion. So, fair to minority groups and in many ways of defining them, which is computational or based on existing, affirmative action rules or whatever. And on the other hand, there was all these policymakers and lawyers that said, we don't trust you. We don't think you, it's not that we don't even think that you know what you're doing, but we don't think that you have thought about the issues enough. So maybe you did, maybe you didn't, we don't trust you. The principle was that ungoverned, data-driven assessments are creating new forms of stigma, disparate impact, and group discrimination. So the operating word here is that they felt that this whole industry of coming up with machine learning algorithms that make these sort of important societal decisions is completely ungoverned. Now, and then, the notion of governance, so this, one of the participants there, someone who used to be the head of the Harvard Law School, was that the way she would define governance is that it would be some sort of participatory process, okay, responsive, inclusive, follow the rule of law, accurate and efficient. And she said that her feeling was that algorithms were only accurate and efficient, but there's no, that you can govern. I mean, you can sort of maybe see if it's accurate with respect to old data. It does the same, that predictions in the same way that old data says, and how fast it works, but there's no other, in no sense, these other things are being satisfied. Now we are, in theoretical computer science, we're mathematicians. What does this mean? What is this participatory, responsive, inclusive? I don't know. So as a computer scientist, okay, what are the kind of questions that can come up though? How would I think about it? So, so what I did here is I developed it as thoughts or questions that come up during the training, post and future. Okay, so let's say there's a stage where somebody's coming up with an algorithm to decide bail. So this is what I mean by during the development. Usually they have access to past data. So they see profiles of people who were up for bail, whether they were given bail or not, and whether during this time they committed a crime or they didn't show up for trial. So this is like the data. And the question, of course, is what kind of data? Is it good data? Is it bad data? Is it bias itself already? And also, if I'm using randomness during the development, so me as a developer, where is this randomness coming from? How important it is in development of the algorithm? There could be many other questions you could ask, but these are examples of questions one may ask as a computer, as a theory person. Another question is post-development. Okay, so now let's say that the algorithm has been developed. Okay, and it's usually companies are going to develop these algorithms. Now the question is, it has to be verified. How do you verify actually that this algorithm that's given to you and supposedly was trained with respect to the past distribution data that is acceptable, that it actually works? Okay, what does it mean? And then, more kind of interesting to me, and what I'll talk about here is, what does it mean to work? Okay, so you probably all took Introduction to Algorithms as an undergraduate. And that's wonderful. We know what the function is, we know what the inputs are for sorting, we know what the outputs are, we know what it means to be correct, and then we develop fast algorithms. Here the story is very different, right? What does it even mean to be accurate? What does it mean to be fair and so forth? So, and other questions you can ask, do you have open access to these machine learning algorithms? Often the company that develops it doesn't want to give open access. They say, we want to keep the rights. Can you test the accuracy of these algorithms, black box access, for example? Do you have access to historical data to check this against? How much? Okay, so the question of also verification, do you have to retrain the algorithm, or can you have access to a lot less data than before? And again, the most important question is, in what formal sense are we verifying it? And then once you're done with that, let's say the algorithm was developed, you verified that it's accurate, okay, according to some measure that we have to define of what it means to verify that it's accurate. And now you want to use it. However, the population changes, the data changes, there are future distributions. They're not necessarily the past distributions. And does your algorithm generalize, right? So if it's an unseen distribution, what can you say about your algorithm with respect to future distribution? Is it robust? Suppose the distribution is adversarial, and is it fair? Maybe there was very little data on distributions that you're going to, minority distributions or distributions you're going to see in the future. So these are all totally theoretical questions, okay? But this is an amazing, if I had to choose a period to be a graduate student, this is a really good one. Okay, I think there's so many theory questions to ask. So what I'm going to speak about is some work that I did on verification and robustness, and some of it is newer than the others. These are the 3 papers. This is from 21. And here we define what it means to verify. It's one definition, one aspect. And then another work, which talks about this issue of future distributions, and how do you know that your algorithm works with respect to future distribution, given that it was trained on past data. And then this last work, which is newer, I guess it's not in submission anymore. This was in PNAS a few months ago. And that is, what if you don't have enough data? Okay, what if you have data of an old distribution, but you have to make conclusions about a future distribution? Can you reuse the data and give some sort of formal guarantees? But I'll spend most of my time talking about these two. So, so there's this very famous paper, which probably a lot of you have seen, but it's very kind of intuitive. This is a paper by Valiant, also a theoretical computer scientist from 1984, where he gave a formal definition for what it means to be learning. He calls it packed, probabilistically, and approximately correct. It is, in essence, all the, it has in it a lot of what machine learning aims at. So what does he say? He says, oh, my son is calling, you see. No, we cannot do that now. So he says, given a whole bunch of, say there is some concept class, sorry, C and F are the same here, that's a mistake. Say there's some concept class, decision trees, I don't know, neural nets, hyperplanes, maybe just a linear line that you're trying to learn, okay? But you don't know, what do you know? You know examples. So somebody gives you X could be a high dimensional vector, and then there's the function of X, this should be F, and let's say it's 0, 1, it's just a prediction whether this guy should go free or stay in jail, or it could be accepted to school, not accepted to school. Now this is could be much more general. It doesn't have to be 0, 1, could be some finite set, could be a real function, could be like a probability, but let's just say 0, 1, and you're given and all of these X's are drawn according to some distribution. So there's some distribution P, where I get a lot of examples of X chosen in P and then labeled by this F, and I try to come up with an algorithm or an hypothesis H. So H is kind of a proxy for F, where H is going to label X's from now on. And I want to say that there's certain loss of this H. So this is when H and F disagree. So F is really the ground truth. H is what I managed to come up with. Sometimes it agrees, sometimes it doesn't agree. And when the fraction of disagreement is what I call a loss, and it's all with respect to distribution P. Is that? Yeah. So the requirement here is, because this is parameterized, is this loss should be small with high probability. Okay. And back to what we are talking about. Now, I want to, in some sense, what I'm saying is, okay, so if this is my definition of machine learning, how do I address this societal issue? Like, how do I know? And we're talking about verification. How do I know that when the company developed this algorithm that's a proxy for pack learning, that they gave me a good product? Okay, so there's some lessons to be learned to answer this question is from electronic voting. It seems like totally like a segue, but let me explain the connection. And that is that electronic voting is one of these fields also where it's grounded in reality. And people have tried to kind of jump over in the beginning, they tried, let's do electronic voting, electronic voting machines. They didn't really mean sending electronic ballot. And very quickly, they saw there were mistakes. Like there were counties where the number, it just made no sense. You know, if you counted the number of votes and you counted, it just was wrong. Sometimes the wrong number of votes were counted. Sometimes the outcome was wrong. And as a result of that, fairly quickly, they took some voting machines, these electronic voting machines, and they ruled them out. And the lesson for this, okay, which is the lesson that we'll use in the context of our question of verifying machine learning, was that there's no way to really check that these machines are going to work, to give you a guarantee that the machine works. But in short of that, what we want to be able to do is detect a mistake. So we just want to. So they're saying a voting system is software independent if an undetected change or error in the software or hardware, you know, cannot cause an undetectable change or error in an election outcome. So they're saying, you know, might be there's an error in the box, in the software, we don't know, but this cannot go undetected. So if you think about the analogy to what we've been talking about, some company came up with a bail algorithm, okay? I'm not going to really be able to give you a guarantee if it's correct or incorrect, but I should be able to tell, meaning if the software works there, but I should, when it makes an error, I should be able to tell. My higher order lesson from this, okay, is that we need a verification mechanism. Yeah.
What kind of error are we talking about? An algorithmic coding error or an error, or doesn't even make sense, like the prediction?
So the truth is, Shubhang, that as I'm giving this slide, I realized it should not be here. So in other words, in the context of voting, what they meant is a coding error. And although it could be also algorithmic error. But what they said, I put all of that aside. I want to make absolutely sure that I can tell a mistake if the election has, if it's wrong, somehow. Okay, so they're saying you have to come up with a verification mechanism which is independent of the machine, in the coding, the algorithm we use, but somehow I'll be able to verify that the result of the election is correct. Okay, so the important part was that there will be some verification mechanism which is independent of that, of the details of the algorithm. So in some sense, it's preaching to the converted. It's a lesson from voting, but I'm already saying I started the talk saying that this is what I want, and I'm telling you that it's inspired from voting. So that's why I'm saying it probably doesn't belong here. But thank you for the question. So where do we get so let's go to this question. What kind of verification mechanism are we going to have for machine learning? So there's lots of verification tools out there. You know, Shvangi's worked on them. Elet, I've worked on them. There is program verification, which you may have heard about. So it's like formal methods for proving that a program is correct. There's interactive proofs for program delegation. There's zero knowledge interactive proofs. There's non-interactive zero knowledge proofs, SNARKs. I think, I don't know if somebody's talking about it in this conference or not. And the question is this any good for verifying machine learning? Okay, can we use one of these old tools, okay, to verify machine learning? So many of them, there's such great mathematics. Can we verify machine learning with them? And the problem is that all of these things are for, they prove that the program of X, for example, running the program on some input X will really give you the right answer, will equal to f of X. But it is for pre-specified f. So we know what the function is. So if we think about an interactive proof of graph isomorphism, we know what graph isomorphism, what it should say yes if the two graphs have an isomorphism. To say no if they don't have an isomorphism with them. Or if it's the sorting example, the program should output the sorted list on any input. But the whole point in machine learning is that we don't know what the ground truth is. So what are we supposed to verify? So none of these tools are really going to work. That's just not going to work. We have to define a new setting. Okay, so what we're going to do is we're going to start from interactive proofs, okay, and we're going to modify it so that it makes sense for machine learning. We're going to modify the definition. So interactive proofs, you've got a prover algorithm, you have a verifier algorithm, there's a question and answer mechanism, and there's a mathematical claim, and at the end, the verifier says, I accept or reject the mathematical claim, and we have two requirements, completeness and soundness. Completeness means that if the theorem is true, if the claim here is true, whichever it is, then the prover should be convinced, the verifier should be convinced. And if the theorem is false, then no matter what the strategy of the prover is, he will not be able to trick the verifier to accept with high probability. Okay, but again, this is not suitable for us because the mathematical claim is not clear. It's not that the program of on x is equal to f of x. So there's lots of history here. There's lots of questions in each one of these fields. Okay, but none of them are really suitable for us. And I'm kind of using this talk also to give you some, l'arbitz Torah, to also tell you that this is a field that extremely rich. There's lots of systems, and this is a beautiful theorem that's based actually on quantum entanglement that has resolved some problems in classical mathematics that have nothing to do with quantum. So we're going to deviate here. So now comes a new definition, and that is we still have a prover and verifier, except our prover, in addition to just what we thought of before, we want to think of it as a learner. So it's that company that did the machine learning, and now it's job to prove to the other entity, which is independent of it, in the spirit of the election story, that whatever model they came with, this I'll call it an hypothesis. So they came up with H, which is a proxy for the ground truth. Okay, it's a good one. Okay, so that's what is the access, what is the input? Whereas before the input was a mathematical theorem that they wanted to check that it's correct or that a computation was done correctly. Now the input is access to a distribution. So what is the past distribution? There's these x's and there's the f of x's, which is supposed to be the ground truth. And I want to convince you something about this hypothesis. And let's check what it is that I want to convince you of. So that's I'm going to give in the next few steps. But I want to say that the learner and the verifier, both of them have access to distribution, but it could be that their access is different. So whereas the company that developed the learning algorithm, it has access to lots of data, it makes sense that the verifying entity would have access to less data. Yes?
Yeah, I'm just wondering, so are we proving accuracy here, or are we proving, okay, why not also?
There you go.
So regarding this function f, what is this proof about? Is it about proving how accurate it is with this function x and function f, or if f is the fairness function?
No. Okay, good question. Very good question. I'm going to define what we mean. So I haven't defined it yet. Okay, so this f exists supposedly in the sky. And that it's not a question of f being fair or not. F is, in the case of Baal, for example, f is some underground, that's the truth. So in the case of Baal, you could say, well, what does it mean that it's the truth? The truth is as defined by the past, that somehow we are believing that these decisions that were made in the past are decisions we want to mimic. So that's the truth. That's what judges would have done, okay? And I don't know if they did the right thing, the wrong thing, that's what they would have done. And I want to have an automatic system that will do this instead of the judges. Yes.
So what would be the difference between the learning algorithm and the verification algorithm? Just data?
Okay, so great. So you can define lots of differences. One difference that I want to focus on the results that we did is that there could be a quantitative or qualitative difference. So there are sets of results for quantitative and qualitative. By quantitative, I mean that let's say this guy gets a whole bunch of random samples, and so there's the verifier, but the verifier random samples are little of the number of the verifier's random samples are much, much smaller than, so in a significant way.
So my question is, if we have a better verification algorithm, why can't we just use that as if you have a better algorithm that verifies machine learning algorithm, then whatever that is doing, why can't we just replace the learning algorithm with this algorithm? And
because the learning algorithm has learned something, it's going to give information to the verifier to use, okay, in order for its verification. It could be that it was a very complicated, let's think about it like this. Suppose the prover for a minute was unbounded, okay? It's not. It's using more examples, okay? But with this use of the more examples, it comes up with some short information, which is incredibly useful, that enables me now to do verification. So it's the larger, it's the access to more examples and maybe more time that enables me to come up with this advice, short string that I send to the verifier. So the thing is, in fact, this is going to be the main issue. right? In order to say the verification is an interesting question, this is the main issue. That is, can you show that you could verify with a lot less samples than you could learn? Can you show maybe that even the type of access you need is lower quality? So for example, one of the results that we show is that there's some concept classes like decision trees, where in order to learn them, you actually need more than just random samples. You need membership queries, at least in theory. So you need to choose X of your choosing and then get back F of X. And so that's what's called membership queries, and not just random sample of X of X. But so you could ask, maybe you could verify just with random samples and you don't have to do membership queries. And if you'd like to have a story in your head, membership, let's say in a medical setting, a membership query might be, you could take an X and do a medical trial and then get back F of X. And based on all this, you now are saying this is a tool. But the person or the entity that's verifying it might just have samples of the history of procedures done, outcome. Patient and what you've decided, what procedure to do. So I got to tell you that not everybody does research the way I do. So for me, the narrative is very important. That's a little related to yesterday. So I love stories, and I think it's very hard for me to work on any problem unless there's some sort of story behind it that motivates it. But that's not necessarily true for everybody. Some people, they like to have a very nice, well-defined question. There's no story. And that's, I think, more true for theorists and mathematicians. Not true for me. So I can give you a story about anything, but I encourage you to keep on asking me the formal thing. So here's the definition. So the definition is for pack verification is, again, I have a classified hypothesis, and I say that it's pack verifiable, okay, if there exists a verifier, such that for all distribution P, okay, if I look at the loss function with respect to this distribution, okay? So loss, again, as we said before, I called it loss, now I call it L, is a difference between H and F. But now I'm not going to call it F, I just call it like whatever the label was. So there's the history, and X was labeled with Y. And I say, and I come up with an H. And there's a reason why I'm not writing as X, F of X, because it could be that there isn't an F, there isn't a ground truth that can be described as a decision tree. Could be that F is so complicated, and I want to come up with a decision tree, so the best one that captures F. So what do I have? I have access to X and Y's, and I want to come with an hypothesis that will make the least mistakes with respect to Y. Okay, and let's say that the opt here is the smallest loss I can get. So out of all the decision trees, I'm thinking about these H's, all possible H's in the class that my outputs are going to be in. This is going to be the smallest loss. So the smallest disagreement. So what I want now is to have the following requirements. Completeness is that there exists a prover, so a learner, that can prove to me such that the probability to verify accepts, and indeed the loss of, this is little h here. So just not to confuse you too much. Okay, so in other words, I outputted, if you remember the story, there was the learner and the verifier, he sends them over a hypothesis. So this is this hypothesis that he sends over H, yes.
Just to clarify the order of quantifiers, is it the same verifier for all epsilon delta? That you could pick, there exists a verifier.
That's a great question. In the theorem that we prove, it's the same verifier, so just its performance varies according to epsilon and delta, but you could imagine that for every epsilon delta, you have a different verifier. I don't know that it would give you some strength, but yeah, good question. So the completeness is that if indeed the H, okay, that you can come up with H's such that their loss is not too far from optimal. So optimal is the smallest loss. Your hypothesis maybe didn't reach the optimal, but not too far from the optimal. Okay, then the verifier will accept with high probability. And soundness says no matter what that prover strategy company is, okay, then if the H that they came up with is far away from the optimal, so the error that it makes is far away from the best error that can be made for little h in the hypothesis class, then you reject. And in addition, double efficiency, which can be defined, as I said, either less samples, or maybe samples of a different type. I'm just going to leave it vague as double efficiency. Okay. So it's let's see for a second. Let's just like see, for example, how this would be worked in a setting. So the verifier will outsource some machine learning task to the prover. The prover then collects lots of high quality data, trains some good machine learning model, little h, okay? And the verifier receives little h. And now let's say he tested it on the samples that he has, and he says accuracy 80%. Should he accept it according to our definition? Okay. Well, you know, if indeed it was the case, okay, that the optimal is 0, what does that mean? It means there is an h that would lose 0. It's an identical, you know, let's say that it's an identical to the to this ground truth. There exists a decision tree that would be absolutely correct, okay? Then I'm saying that's a pretty good procedure. I take 1 over epsilon, okay? The parameter epsilon is what I'm supposed to achieve, random samples, and I accept h if it classifies all the samples correctly, right? Because there is a 0, okay? Then I just check to see if I made few errors or didn't make few errors, and according to that, you know, I can prove this theorem very quickly, right? So if it was 0, I'll always accept. If it was more than epsilon, then I reject with constant probability. And then there's not much separation between verification and learning. Yes.
How does the verifier know that it's this case? Like it knows that there is a.
In fact, this is not going to be an interesting case. So I don't want to answer that because I'm going to say that the only interesting case is going to be the agnostic one, where your question is it's supposing, it's an assumption. You're saying in the case that's a good procedure, but let's assume that's not the case because it's never going to be the case. So there's never really going to be a simple, nice, clean model like a decision tree that's going to capture the underlying truth. So in fact, then now it's going to start being interesting because what is it we want? What we need to check really is the loss of the h that I have in my hands, okay, is less than or equal than the optimal plus epsilon. So this is easy to estimate. What is the loss of the thing that I have? I just test it on samples, see how well it does, okay? But how do I check? How do I verify that this is pretty close to the best that can be done by an amount of epsilon? I mean, so in other words, it's not that I'm going to, it's not that I'm going to, this is hard to estimate and I'm not going to try to estimate. But what I need to verify is this inequality. Okay. So that whatever I got in my hands is not too far from the best, okay? And what we show for this definition, so that's the definition. So I hope that whoever asked here what the definition is, I think it's the third row. Yeah, well, what am I proving? I'm proving theorems with respect to this definition, that the prover gives an h, and I checked the accuracy of the h in the following sense, that if h is close to optimal, close by epsilon, then with high probability I'll accept, and if h is far more than epsilon from the best that can be done, then with high probability I reject. And what we show basically, and now the interesting question is, can you really verify any better than learn? And first of all, we show that you can, if you just talk about less samples, sometimes you can, depends on the concept class, and sometimes you can't, okay? But I think the more interesting result is this qualitative separation, which is so we found a class of hypotheses, which essentially correspond to decision trees, but in the language of more theoretical computer science, is if you look at functions f, underlying functions f, the ground truth, they look, and we think of them as Boolean functions. They are what we call t-sparse. So if you write the Fourier representation of them, the sort of Fourier coefficients where the weight of the function lies on, and it's what we call t-sparse. So there might be only one coefficient that's dominant in the decision, or there's, in any case, at least t-sparse. So this is the kind of functions that have been studied in computer science and machine learning. There's this famous paper by Kushelevitz and Mansour that shows how to learn such functions, okay, from access to the function, xf of x. And what they show is they use membership queries. So if you can give x and get f of x, they can learn this representation of the function, these Fourier coefficients. And this decision trees are captured by that. In addition, essentially, there's a proof that you need membership queries. What do I mean by a proof? it has been shown that unless that H is not pack learnable from random samples, but it is learnable from membership queries, unless a problem called learning parity with noise is easy. I'm not going to say what that is. There's some mathematical problem people have worked on a long time, which is learning parity with noise. It's also used in cryptography. We believe it's hard. If indeed it is hard, there's no way that random samples are enough. To learn these kind of functions, you need to really choose the X and get f of X back. You're doing some sort of binary search there. So you have X and then you have X over 2 and X over 4, and you always follow these X's you need to find f of X. Why is that interesting to me? Because we did show that H is pack verifiable by a prover that needs membership queries, but the verifier doesn't. So the verifier, it's enough for him to have random samples. So that's a qualitative difference between the prover and the verifier. So it's easier to verify. Again, the verifier is independent of the prover. He just asks questions from the prover and the prover must answer. And you are sort of checking, the key idea is that what the verifier really is doing is not learning the concept again. He is just checking inconsistencies of the prover. So in a sense, you would like to say you want to reduce the problem of the prover may be cheating in the sense that the hypothesis it came up with is much further from, the approximation is much worse than this underlying function that by epsilon, okay, that's what he claims, and you are going to catch him in a lie if that's not the case. So there's going to be some protocol where at the end you'll, in some sense, the burden of the proof is on the learner. We say there is a procedure you can follow to convince me to accept. But if you don't follow the procedure and your H, in fact, is not a good one, I will catch you. Now yeah.
Way of separating the power of
In this particular case?
just in general, just random access versus.
So there are quantitative separations, but it depends on the class of hypothesis. So when I say not always, this is really sort of the kind of theory, cheap thing, which one hates. And that is you show that if you define these hypothesis class randomly, there is a way, there are hypothesis classes where you show there cannot be quantitative separation, but then there are some sort of more natural ones where there are sort of a lot thresholds and a line, things of that sort. Okay. All right. So in some sense, after my entire build-up, like we're going to really change the world, maybe that you don't like it in the sense that this is a formal mathematical definition. It captures something, okay? It doesn't capture that this is absolutely the fair hypothesis and so forth. But I think that the more important message to you is that you could talk about other properties like fairness, like robustness, like whatever it is you want, okay? Define them formally and then try to show a protocol to verify. And I think that's the beauty of this is that it's you can define what you are going to show, okay? Okay, so there's a bunch of questions about this before I move on to robustness. So the algorithm that we gave, for example, for that last result, accesses this H in a black box manner. And I feel that's a good thing because sometimes these companies that learn, it is a good thing. It's better, it's a stronger result if you access it in a black box manner than in a white box. And it also satisfies sort of the reality that often people don't want to just give you the code. Maybe they commit to the code. So maybe, and then they prove to you that if they ran this code on an X that you are asking them, this is what they would give, maybe in a zero knowledge way or something like that. It's interesting that I motivated this whole thing with a Bail example, right? And you would think if you really wanted to bring this to practice, this is very different than legal norms, if I gave a zero knowledge proof that something is true, how would the courts actually accept that? Is this acceptable? Is not acceptable? Very interesting question. Different research area. How our notions, play with what a norm is in a courtroom. Another question you could ask is where is all this randomness coming from? Of the verifier, of the prover? Prover I can't control, but verifier I can. But I want to make sure that the randomness I'm using is good enough to catch a mistake. And again, when you transfer this to the real world, I think nobody pays any attention to those questions, except in cryptography, where we have examples of people generating RSA keys using some sort of randomness procedure that it turned out that lots and lots of the keys were in the internet, where like 2 primes, like P and Q, where everybody had the same P in different Qs. Now, very simple calculation is you take P times Q and P times Q prime, you do a GCD algorithm, greatest common divisor, P comes out. So that's not secure. So, and the point is that they generated that P using randomness, which was kind of shared by everybody. So these are the questions that people are not asking, but I think, they probably should ask. Okay, and finally, just about that legal thing that I said, that whether they would accept it or not, if I give evidence or I give zero knowledge proof, that's the least of it. It's not even clear how courts will address probabilistic reasoning. So, there's a lot of kind of interesting cases in the past. There's this article, Statistics in Court, Incorrect Probabilities, which is a lot of fun to read, where cases where people were arguing in court say that probability, in order to accuse someone, they're saying they were faulty, let's say in a medical case, saying because the chance that this thing would have happened by itself, okay, is extremely low. And the reason, and the way they would argue chances is by using sort of like a product law. You say, what's the probability that this would happen, and this would happen, and this would happen? Now, these things aren't actually independent. In a lot of these cases, you can see that they're not independent at all. So to use the product law to get a very, very small probability at the end that something would happen unless there was bad intention is just not the right way to argue. So we are going to then argue about zero knowledge proofs, about probability of learning, about, so learning to evaluate statistics is key. I think in any kind of court setting, and I bet the future is going to see a lot more statisticians testifying or maybe even understanding by people with legal training about what do probabilities mean, at least to detect possible mistakes, to know that there's a product law and there's a question of independence. Okay, I'm done with this. I'm going to move on to robustness, okay? So robustness was the question whether the distribution that I have in the past and I learned, how is that going to fare with respect to future distribution? And they might be adversarial or not. Let's just talk about it as future distribution. So again, remember that definition. Given a bunch of examples, that pack learning. From the past, I want you to do as well on those same distribution. The thing is, so the training distribution and the testing distribution are the same in the definition. I mean, Valiant realized, it's kind of obvious that if I haven't seen any example according to this distribution, I can't require the algorithm to do well, right? So if I saw distribution P, I will do well with respect to distribution P. But this is just not the case. So there's something called covariate shift. That's where the distribution is shifted. So it's really just a new distribution. So for example, people give this example about COVID, that there's sort of what a normal lung would look like prior to COVID and what it looks like now where most of us have had COVID. So you don't understand how much of a relief this is. Because for 2.5 years, I've been waiting for that red line on the test case. Finally, it arrives. Okay. It's not like I haven't turned into a beast or something. But these are very different. So if you have something to diagnose lung cancer on those old photos, they're not going to really work necessarily on the new ones. Same thing is about, US data. This is how you guys write a one. This is how you would write a one internationally. That's how I learned to write a one. What if you have a thing trained on that? How is it going to do? So these are natural kind of shifts. There's no adversary intended. It's just a different data set at this point, which is related, but not the same. And this is on one hand, and then there's this whole research in machine learning about adversarial examples. Somebody just wants to feed into the machine learning algorithm some input that's going to trick it. Okay, so that's a much worse case. So there's the test, there's the distribution you learned on, and then there's the distribution you're tested on, and somebody has actually tweaked it, especially to fool you. So it's not just lung pictures that have changed or numerals in Israel versus the US. And what the typical machine learning approach is that they say, I'm going to make, and this is already a lot of progress in the last 4 or 5 years, they say, I'm going to make my algorithm robust to what's called perturbations. Perturbations is the adversaries, surely what they've done is that they took old distribution and they tweaked it a little bit in order to trick me. And for that kind of adversary who was into like perturbing natural inputs, I'm going to make my algorithm robust. The thing is that that really is not what modern day adversaries do. So I think there's this famous picture of pandas where they put a little barcode on it and then everything changes. It becomes, I don't know, a plane or whatever. The point being is putting a barcode on a picture is not a natural perturbation, obviously. So thinking sort of as a worst case analysis or cryptographer, we want to say that protecting machine learning against adversary attacks or making it generalizable to general distributions, okay, should be with the idea in mind is that it's not that the adversary is cooperating with you because they want you to publish papers. The adversary is doing what they're doing, and you can't assume how the adversary behaves. Okay, so this is what we'll do in the second half of the talk, okay? So here's going to be the working example. The working example is that we don't talk about neural nets or decision trees, something much simpler than that. I get examples on a plane, points, which are labeled either pluses or minuses, and there is some way to define pluses and minuses, which is just a line, okay, or hyperplane, a half space. And when the training distribution, so then comes these points, which are the test, and let's say they're distributed in the same distribution as before, then no problem. I run my machine learning algorithm, I come up with an age. It's not F, but as long as these black dots, which are the testing rather than the training, distribute this way, it's going to be a good pack learning output. But what happens if it's not the case? So the black dots now some are distributed like before, but all of them are in here. And I've never seen any example in this region, in this gray region. So F1 and F2 are really just as good as each other as my candidate, what I'm trying to aim at. So the point of this slide is saying is that when the training distribution is different than the test distribution, which is the case here because there's a lot of dots here, yeah, then it's impossible. It's not a question that I am not smart enough. It's just impossible. There's not enough information to distinguish between F1 and F2. So what we're going to do, we're going to define again a new model to add this, to address this, is that first of all, we're going to allow the classifier to either, this H that I'm coming up with is going to either say yes, no, or I abstain. So I've added I abstain into the mix. And moreover, it turns out that that's, and which you must, okay, that's not even going to be enough. For the kind of results that I want to prove, I'm going to show that even that's not good enough because, let's say it's an adversary and they know that I've answered incorrectly on this test data. Then, so I'm thinking about an adversary that actually knows the F and even knows the H that I'm using. And now it's giving me future points to classify. Then why not bunch all their future queries right next to a mistake? So they're going to make mistakes all the time. Okay, so what I'm going to add, I'm going to say, not only that I allow the algorithm to say yes, no, or I abstain, which was not allowed before, but I'm also going to require that my algorithm has access to unlabeled test examples. So let's think of it this way. Let me give you a story. I think we're talking about classifying YouTube videos as offensive or not offensive, okay? And this is something that's done by YouTube when they accept a YouTube thing to post. So there's all the past examples of YouTubes which were offensive, not offensive. That's the labeled data. Now come new YouTubes. And what can I do? Maybe now they're like really very tricky and they can get around whatever mechanism that was detecting pornography or hate speech or whatever, okay? What I'm saying is before I post them or before I decide whether this is a yes, no, or I abstain, I want to see for a while, I'm going to assume that I get for a while a bunch of examples of this new type of YouTube, and only then I'm going to output my classifier or update my classifier. Another example is say you're in a medical procedure setting. So instead of deciding to operate, not to operate, or abstain, okay, you're saying I'm seeing new patients now. They look different. Okay, I'm seeing a whole bunch of, I'm going to have maybe a new procedure. Theoretically speaking, my assumption is, one, I allow myself an easier job. That is, I'm allowed to abstain. And two, in order to make the decision of whether to say yes, no, abstain, I also require the ability to see a whole bunch of examples for the future distribution, unlabeled ones. So in the past, I have x's and f of x. In the future, now I get also a bunch of x primes from the new distribution, which are unlabeled. And now I'm going to output a candidate hypothesis, which can handle examples from this new distribution. Okay, so that's the definition of the model then is, I'm going to call it PQ learning. P for the old distribution, Q for the new distribution. And this is in this paper with Yael and Adam and Omar Motasar, who's a graduate student in Toyota Institute. Again, we're going to be given labeled examples, but we're also going to be given examples for the new, sorry, this should be testing distribution. So let's take. Okay, so yeah.
Decisions on?
No, it's different than that because my new ones, I don't get labels for them. So it's not, but I am delaying the decision. But the decision that I'm delaying is it's going to be a little bit different decision. So in other words, it's not just going to say yes or no, it's also going to allow it to be abstain, which is something that wasn't required before. So the PQ learner is going to have to output an hypothesis and also a description of a set S before he just does the process. S where he says, this is where I answered, this is where I don't. That's just a formal way of saying that he can say, I don't know. So in advance, he's going to say, this is the region where I'm going to give you guarantees, else I will say, I don't know. So I'm going to specify that in advance. So that's a part of the output. Okay. So I'm going to only answer yes or no on X's and S and I abstain everywhere else. And what I will say that a good PQ learner is, so this is what I've described what the inputs are. I've described what the outputs are. Now, what is it that I'm going to define as a good PQ learner? A good PQ learner is one where the rate of abstaining on distribution P, so in other words, if your new distribution and your old distribution are the same, you don't want it to abstain. That would be like he just says, I don't know, the end. Okay, and that's a good no. You want the rate of abstaining on that to be low. You want the rate of error on the future distribution, okay, to also be low. And essentially, in order to bound both of them, what I'm going to say is that I want that the sum of the abstaining and the loss to be less than epsilon. Okay, so in other words, my algorithm is going to sometimes abstain, sometimes going to make errors. I don't want it to make too many abstain and too many errors, and I define it with respect to these different distributions. In some sense, who cares about the past? You really want to care about the future. You want to say that your rate of abstaining is small and the rate of loss is small. So you would like to have Q's here, but the truth is that if you have P that actually implies something about P, if you have about Q, and that that is related to the difference between P and Q, but never mind, that's a detail. Question? Yeah.
You just turn that abstain into a loss on P.
Oh, abstaining is that I said I don't know on P.
If you just add on those points, is that
So
kind of parse it? Instead of, if you just agree to get it wrong on those points.
Yeah.
In P, is that change?
So on the P points, on the P. So in some sense, if I never see P in the future, I don't care if you're right or wrong on it. What I care is if you're right or wrong on the distribution that I will see. And for the H's where I say where I actually give an answer. Maybe, yeah.
Is there a mathematical difference between how abstain P is calculated? So loss is calculated by just the difference between H and F.
I can. My hearing is deteriorating as the lecture goes on. Yeah. Okay.
So loss.
Turn it on.
So loss is calculated by the difference in HX and FX, right?
By
the probability differences between.
Are you asking about what's in the parentheses here?
No, I'm asking what is the what is abstain mathematically formalized? What is the
abstain is
formalization?
the probability that the H on X is different than F of X, where X comes from P.
So why not just like if I just had loss?
No, not different.
Plus loss?
The probability, sorry, the probability that H on X for X is P says I don't know.
Right. So like just if this is the function that we are trying to minimize or whatever, then there is no what is the mathematical difference between loss P plus loss Q versus abstain P plus loss Q? And if it's just an addition of these two terms, then how is it? So how is abstain P plus loss Q different from loss P plus loss Q?
So one is, I think the complement of S is going to be value of abstain also. S has to, this way, is this saying that S has to be a big set?
you're asking why this is gonna, why not just talk about loss?
Yeah, how is this
Why-
particular function different from loss P plus?
Yeah,
loss?
you're saying why? Why don't you just talk, always say yes or no and
Right.
okay, well, the reason is because I don't know how to get that. First of all, the quantity is definitely different, and I don't know how to achieve the loss everywhere being small. And those pictures where I showed that sometimes I never got data on Q, or the data that I got is very close to something that always going to go wrong, on to show that I can't achieve that.
Right, but I don't have, so that would make sense to me if the abstain had like less weightage, or if this was a weighted
So what I'm
function.
saying is, if I could, if let's say that P and Q are sort of disjoined, there's no support in common, okay? It could be that on Q, I always say I don't know. In fact, it should be. I no idea. I don't know. So I'm not sure then that your thing is going to, I'm not sure how your measure would behave, if I understood what you're proposing. Because you want that, in that case, that would be terrible. Right? Because I will have a huge loss, because there is a truth. There is a truth to these examples. There is an F. There's a yes and correct yes and no, but I have no chance of getting it.
Okay.
Maybe we'll talk afterwards, because I don't understand you. And I'm sure you're right and I'm wrong, but I just don't know.
No.
Okay. But something you didn't ask is it even a reasonable thing? Yeah, 5 minutes. Is it a reasonable thing to assume that I have access to test distribution? But it's not reasonable. And I claim it is very reasonable. And the reason is because, first of all, sometimes that's exactly what I want. I want to have a guarantee on particular spots in the future, and I know what they are. And before I actually go about and sort of the transductive, it's not a distribution type of guarantee, but it's a guarantee for specific inputs that I get afterwards. And another thing is that you could always do things in retrospect, right? So you might have an H, it's not a very good one, okay? And after a while, you can retrain it to say, okay, I've seen enough examples, unlabeled, okay? Now I'm going to adopt assuming that this is how it's going to keep on going, I'm going to adopt my H. So the theorems are the following, and maybe I'll have a minute to flash the algorithm. So the theorem is that you can actually do this. So if the class is pack learnable in a setting, this time we're talking actually in a setting where it's realizable. So there is a class that can be realized. There is in my class H, it's in the same class where the underground truth F comes from. And there is a way to do it, pack learning. There's like an empirical risk minimization or some kind of algorithm. I can use that algorithm as a subroutine to output such that for every Q, every distribution, now, no restriction that it was obtained by perturbations or anything like that. So for every P and every Q, I can output this learner in a set S where it's going to be restricted to. So with high probability, the abstain and loss is less than this bound to hide some log factors. But the point being is that if you compare this to what can be do for pack learning, it's D over N. Here it's only square root. So your error is not as good. Or another way to say it, you need more samples to get the same error. So you need like N squared over D rather than N, proportional to N squared rather than N samples, where N is the amount of training that examples that you got and the amount of examples you're going to get for test. So here is just apropos this thing that I mentioned about abstaining on Q, and essentially you can show that the rate of abstaining on Q is less than abstaining on P plus the distance between them. So what about white box? So this was just a shift from P to Q, but what about the really tough one, where the adversary knows what your hypothesis is? I don't know, maybe it works in YouTube. He knows what the underground truth is. And he says, I am now going to advise my friends to submit YouTube, which can avoid the whole thing. Then we say, well, you can get results there as well. You could think of it as 2 stages. First, the learner outputs an H. And only then, so YouTube has an H, and then an all-knowing, interior adversary outputs some test examples. He says, on this, you're going to be wrong. Okay, but I'm going to use those test examples as my input, right? Because I said that I get test examples. So in the second stage, I will output as I promised, hypothesis, which is restricted to some set S, and the description of the set S. And the theorem is that, again, you can, for such an adversary, who gets his input. You can even think about it as getting a bunch of labels and having some test and even that maybe was obtained by some naive person, then altering them to be bad ones because based on their knowledge of H and F. Maybe it's not written exactly in a way that's easy to read. Again, the loss plus abstain error here is loss is going to be less than this bound. What does the algorithm look like? So just I know I've maybe a minute, just to get a sense that there is an algorithm, and it looks like something like this. So here's the example that we were using. So first, you're going to learn a classifier. You get a bunch of training examples. You ignore this whole new thing about wanting to see the future and all that. And you do your machine learning, and you have an empirical risk minimizer, and it gives you some. It gives you some hypothesis, okay, in the class. Yes, over here. Some hypothesis in the class. C used to be H, whatever. It gives you a decision tree, okay? It gives you some classifier. And now this is not going to be a good classifier for the future. That's what we're going to take this guy and we're going to modify it. The way we're going to modify it is actually, we're not going to replace it with a new H, but we're going to define S. So we're going to essentially define where is this thing going to be good at and can be used to say yes and no, and when you should abstain. So in some sense, the whole thing is going to be how to figure out where to abstain. And so that you can get that thing that I promised, that abstaining plus loss is low. So in other words, if you're just running it the old pack way, it's still going to be as good as a pack learner. You don't want to abstain in that case. All right, so the idea is that you are going to go some sort of through iterative process where you are going to use the same pack learning procedure, like the empirical risk minimizer that gave you C, and you're going to use it again and again, but on a different distribution. And you're going to, let's look at the first stage. You find you're using the same algorithm, you find a classifier C1, okay? So there was the H that I already found. I'm trying to figure out the region where it should abstain. I find a new classifier with the following requirements, that it's equal to H for all the training set. So I'm saying this new classifier actually is going to behave as good as the best one on the training set, but I wanted to disagree significantly on those points which are already in S. So S right now is everything, okay, in C, when we do C1. So I'm saying I wanted to be really have the maximal disagreement, okay, on things that I haven't seen. And then I define my set to be those places. This S is going to keep on growing. To begin with, it's going to be those X's where H and C0 agree. So I've thrown away all the places where they disagree. And now I'm going to do this again, okay? But the disagreement here is on this S, when S has been newly defined. So in other words, what I'm doing is I'm saying, well, I don't want to make mistakes, okay? I want, in the case of mistakes, to abstain. So let's see how much, if I'm doing really well but still disagreeing, those are the places that I should abstain on. The rest of them, I keep doing this iteratively and can show that this thing will sort of stabilize after not a too large. This is another result here. How much time does this process take? So linear time, and at that point, I can guarantee the theorem that I have outlined. Now, what's interesting about this is you have to change this algorithm somewhat. But you can get results off of for unsupervised learning. So unsupervised learning means that even in the training phase, I was just getting X's. I wasn't getting labels. And it could be now, I had some wonderful algorithm in an unsupervised setting, maybe a clustering algorithm or something. And in the future, I'm getting new points, but they're from some other distribution whatsoever. So even there, I can talk about using my previous classifier and then saying, I don't know. So it turns out you can do this as well. But it's you need as a black box, not just empirical risk minimizer, but something heavier. So there's a lot of meat here. But I think more important than that is that my co-author, Adam, he has other papers where they don't, I see that there was a dissatisfaction with our formula of abstain plus, at least by you, and loss. So they've changed it to sort of have weighted answer. So you give always an answer, but you have a confidence in the answer. So it's like yes, no, and you 50% in some sense, do what you like. But and then the formula that they're trying to do is to sort of minimize the error with respect to this weighted definition. And they have a different algorithm also to achieve it. Okay, so there's extensions. And this is the work that I mentioned by Kalai and Kanade, where they have some penalty function. When you think of it as a penalty function, what is another way to think about it? Is it when you abstain and you shouldn't have, or something, or when you make mistakes and you shouldn't have, they have some function, and they want to minimize that, the penalty that you get. I'm done. I want to just say a word of caution is the fact that you abstain is not the end of the story, because you could say, well, I've done my job, I abstain when I don't see data, goodbye. No, you should collect more data, right? You should collect more data to be fair, to be general and so forth. There's a lot of examples involving actually women and men about, color and gender, and the fact that there's not enough data, then you get the wrong answers. In our case, we just abstain. So everybody's happy, but not abstain. If you want to get through a door, and you are a woman and the only way defines men's faces, say, well, sorry, I can't tell. It's not good enough. So, okay, that's it. So there's lots of questions, I think. I feel that as a cryptographer, at least, we've got plenty of skills to deal with them. And these are some other examples: privacy, safety, fairness, are all these things, freedom of speech are sort of societal values, but they have now a new question when you put algorithms into it, and they require some sort of math formulation. Thank you. Any questions?
So yeah, the final thing was like the abstaining thing. I think it's very powerful in the sense, even in fairness, sometimes we're like, okay, we have not seen this data, what is fair, and then abstaining is like one way for sure. I'm just trying to connect with the fact that there can be distributional changes and how can abstaining. So the thing that you said is like if you have more data or less data in regions, and then in future you can have more data, but in machine learning, often there are like changes even in the feature set. So maybe certain kind of features where a factor saying that they would have a very high salary, but the features have kind of changed, feature including like there are more female or more people from diverse background. So the entire
the definition of X, actually, even the domain set is
different. That can kind of change, and the Y. So yeah.
So it's just an interesting question that you could even, another way to say what you said is that I'm kind of assuming that that I'm maintaining the same F, but I'm not really maintaining the same F even. There's a different domain,
Right.
Still, you might think of these, in this new definition, of these liberties that you can take, where you could abstain, where you could talk about penalties, where you can assume that you have access to data in that setting. But I agree with you that this is really a very basic setting, where you are maintaining F the same across, I think of it as maintaining the same.
Yeah.
That you want the same kind of label, it's just that the data you've seen is different.
Right.
And you're making a good point that maybe even the features and maybe our societal standards have changed, in F, if F decides about going on bail, now we think, going on bail has a different meaning.
Right.
This doesn't capture that.
Okay. Yeah, thank you.
Thank you. Yeah.
A question about the first part of the talk when you talk about like having the verifier. I'm wondering what your thoughts are in terms of how it relates to like this common practice of auditing. And I guess, is auditing just the empirical version of a verifier? But obviously in a lot of like fairness auditing, such like that, you're not taking samples that are like ID at all. You're like crafting these samples that you feel like will reveal bias. So yeah, I'm wondering what your thoughts are in terms of how what you presented relates to this common practice of algorithmic auditing.
No, so I think on an informal level, auditing and verification are exactly the same. On a more formal level, there's an interaction going on here. So when you say auditing, how is it done? That's my question. What does the model allow? Does it, if you can look at H in the, in white box, can you look at black box? Can you have access to the person who trained it to help you out? Here you have access to them. So in addition to giving you access to the H, they also do other things. You're asking questions that you would think that while they were training H, they should keep around in order to be able to answer your questions in the future. In auditing, I don't know if that is allowed. So the intent is the same. We want that at the end. Well, first of all, I don't even know if the intent is the same. The intuitive intent is the same. Does auditing have a definition of what it means to be successful or not? I don't know. I gave you a specific definition. So it's difference one. Difference two, my assumption is that I give you H, now you audit it. You don't have a participation in whoever trained, learned it. But it's often the case that in practice people are very smart and they come up with ideas that maybe later need to be formalized. Not always.
Let's take all other questions offline.
Thank you.
Thank you. We have a quick 15-minute break. I think refreshments are outside.